Does everybody hear me?
Yes.
Okay, thank you. All right, so we are continuing today with magnetic fields from loops, and we're gonna go to more complicated structures. But I have a couple of things that I would like to mention. So number one, in expecting to have a midterm on Wednesday, I'm gonna remind you and I'm gonna put it on. It's not gonna be on Friday next week, it's gonna be on Wednesday, because Friday, there are a lot of people who may wanna go out of town and we wanna have it on Wednesday. Otherwise, I will have to make exceptions and then arrange for people to take it at different times. So it's gonna be Wednesday. In anticipation of that, I decided that all of the office hours, starting today, we are gonna solve different types of problems as practice. So I would, so Monday, Wednesday, and also I'm going to move the Sunday office hours to Saturday. And I will tell you why. All of the students who come to Sunday office hours have not solved their homework. Or most of them, I should not say all, that's most of them. Which means by the time it goes 5:30, there are a lot of students who have not even started solving the homework. So, and I can understand that if you don't understand something very well, you know, how are you gonna start solving it? So we're gonna move the Sunday office hours to Saturdays at the same time, 3:30 to 5:30, but Saturdays. So Monday, Wednesday, and Saturday this week. Well, Saturday I will leave it also for, I mean, anybody can ask me about homework during those times, but I will also do examples, different examples. I can get some from the book, you know, whatever. Some of on my own. And then Monday of the following week, we're gonna also have a review, Monday office hours, right? So that is what we're gonna have. The other thing I've noticed that as we go to symbolic representations, and if you remember what I said about symbolic representation is when you take a 3D structure that may have multiple, say, planes, all right, conducting planes, and they are at different potentials. This is what you have in reality within circuits, all right? You have multiple circuits at different potentials. As a matter of fact, let me see whether it's at some point I had shown you an example here. All right, so look at this. This is reality. What we draw for our problems is like a simplification of some of these things. Now, all of these conductors are not on the same plane, all right? Especially when you see different colors. Different colors imply that there are different conductors on different planes. And sometimes there are 17 different planes that people have, different layers that people have in microelectronics, 17. And they have, that's why they're so small. Because if you had to lay them out all on a surface, it would be a huge thing. This would be like a laptop at a minimum. So all of the electronics here, as I told you, the biggest part is the area where you have your cameras. And here is the battery. The biggest part is the battery here. All of the electronics are here. And one thin sliver here that obviously connects to the battery and the other things. All right, that's it. For that to be this small, people had to develop different techniques. So when you do all of that, what happens? You have your sources. Where is your source? Your source is gonna be a connection to the battery, all right? That's your main source. And then it's gonna come from one or multiple places, depends on how you split it. But then this these lines will bring your currents from the battery, or your charges, if you like, since we're talking about charges here, and or currents. I mean, a charge is a current is like a charge that moves with a velocity, all right? So, and then they're gonna all be distributed. So now, every plane here, because you're going to have charges that accumulate there, whether the charges are moving and some accumulate, I mean, it's a combination. If it's all static, then you're going to have static charges accumulating, all right? Usually, those do not work exactly with static because they send bits. A bit is like a square pulse. Square pulses have high frequencies in there, but even you forget all of these complications and consider statics here. Each one of these metals is at a different potential. And then what do? We cannot design it like this. Obviously, the initial designs do not look like that. The initial designs have a symbolic form, which means we understand where we have resistors, why, where do we lose power along the lines. So a line, for example, will need to have a resistor to represent it. We are going to see that in transmission lines. Let's assume that these conductors are perfect and therefore we don't have resistive loss. All right, so everything goes inside the conductor, all the electrons move without any scattering, therefore we don't lose any energy. So all of the current, let's assume you don't have that early assumption. But then you have capacitances. Every time there are two metals in proximity at different potential, you have a capacitance. Number one, you have inductances. Here I don't see an inductor. Let me see. Is there one? Maybe there is one. I'm not sure this is an inductor, the yellow one here. You see these yellow ones here? All of these, the yellow, which look like this. All of these are capacitors, all right? In this particular part of the circuit. And then these are tabs. There are different levels. 1, 2, 3, and below that 4. You see there are multiple layers below that. But in any case, this here that you try and see those, these are real holes. This is at least they try to put it into a ground potential. But this one is not exactly ground. I mean, let's assume that we can keep it ground. But then this one is at a different potential. This one is at a different potential. These ones are different potential. When these two lines are too close to each other, all right, they will have like similar effects to what you will see here if there are currents flowing. So to be able to design that, you sit down and create a symbolic representation that includes resistors, capacitors, and inductors. That's it. And how do symbolic representations look like? Like an inductor, a resistor, a capacitor. Things that you have seen in your the first class in electric circuits, all right? You guys did that. When was it? Last year? You did last year. Okay. To be able then to make those designs, there are a lot of, there are two things you need to remember, which we are trying in this class. I mean, it's part of the class to make it clear. The fact that you have a ground, like the one we show with the holes, at a one potential, the ground potential, which we assume 0, does not mean that there are no charges there. All right. The fact that you have it is at a 0 potential, but it does not mean that there are no charges. The same way, if you have a line that is connected to ground, yes, it is connected to a 0 potential, but it does not mean that there is no current flowing in the line. All right, so these are fundamental concepts, and I have come to see, and I don't know whether COVID has been the problem, but there is a great weakness among many in this class of understanding the fundamentals. Then second, what I realized yesterday, there are a lot of students who do not know how to find the Thevenin resistance or impedance. They have no clue. And I'm thinking, I'm going to give you a problem where it's going to have to find that. I'm not going to ask for a Thevenin, but I will ask you to find what you see from two ports. That's the Thevenin, all right? When you have a circuit and then you have different batteries and then you want to see what you see from a 2 port. This is how you apply. If you don't know how to do that, you cannot pass this class. And I found in my horror yesterday that there are students who have no idea about this. So I know that there is no idea for, not because they did not do well in class, I'm sure they did well, but because there has been a year maybe when this class was taken. But the only thing that I have to tell you, you have to review something. If there is something fundamental that I'm talking about in this class, but you don't remember it, don't just let go, hoping that you're not going to see it in front of you. There are some fundamental things that if you don't know, your ability to graduate is going to become more and more difficult as in an electrical engineer. And those things that you do early in classes are very fundamental. So I wanted to tell you that because in the homework that I gave you, the last one, I asked you to find capacitances from different points, all right? How you see them. Practically, it's a very, if you write a symbolic representation of the circuit after you identify the capacitors, and you're going to see that I'm going to do some problems like this, then it should be easy to see what you see from two. If you have two capacitors, for example, and one source connected to it, and I'm asking you to see what you see as an impedance or as a capacitance from these 2 points, practically you apply Thevenin's theorem. I just want to say that because I have taught this class multiple times. This is the first time that I saw that there was a group of people who did not remember it. So please go, if you don't remember something, also my advice, which I do, faculty do, that's what I told them yesterday. I am a faculty, I've been teaching 40 years, these kinds of material. You know, a lot of times, and I'm a human being, a lot of times I forget things. So what happens if I come across something that I forget? I go back to the source and I read it again. And I'm a faculty member. I have all kinds of books. I'm not suggesting, but you can find it on the web. If, for example, there is something I need to do and I forget, I go back and review it. I'm not asking a colleague of mine to give me the answer. That's not how we learn. So please, whenever you come across in your homework, that's the opportunity to learn in homework. That's why we give homework. When you come across something that you do not remember, don't come to me and say, how am I going to do that? I had a student who said, tell me how to do this because there is so much material I cannot go through. Well, what do you mean there is so much material you cannot go through? This is what we have to do. I know the pressures. I know what the school, there is so many things you have, but I'm just trying to tell you that because I'm trying to simplify the material down to fundamentals. So I don't make you think that what we are trying to solve are so complex. If you move things down to fundamentals and you remember the fundamentals, the solutions become simple. In any case, that's what I wanted to tell you. I'm going to try to solve as many problems as possible, but expect that in the meter, you're going to see things that we have solved. I decided today, what I'm going to do is the following. I'm not going to give you a new thing to do in the meter. I'm going to pick problems from here and there which we have solved. And this way, I'm going to find out who is studying. Because I'm afraid there are going to be people who will not solve problems which we have solved, either in the homework or in class. And everything that I do in class, I put it up on the web. All right. So keep that in mind. It's not going to be new. I can promise you right now, but it's going to be something then we have solved. And I will expect you to at least be able to see, to know that we have solved it. And then go and copy it if that's what needs to be done. All right. Because I'm afraid there will be a lot of students who will not be able to do that. Okay. That much about it. I hope just I'm giving you, I don't want to worry you, but I just want to give you some, because I worry myself. So I try to take off some of my worries and throw them on you because you can solve my worries too. I mean, all right, so you can help. All right, so review. You remember we saw here one infinite filament. We call, when you hear current filament, means thin, linear, I mean straight line, and long. We don't see the ends of it even if we know that it's closing on itself, all right? It's closing. current cannot start and stop unless it's a source. It can start on a battery and it can end on a battery, but the battery is what closes the circuit. Okay. So what we found is when you have a current that flows like this, then you know, and it's linear, I mean, it's straight. You know that the magnetic field, you can find the direction from the right-hand rule. And the magnetic field, you go here with the lines that you see, all right? Now, some interesting things about, you can say, well, this is too fundamental to see an application. All right, and I'm telling you, you're gonna see from how fundamentals can tell you specific things about applications. So the first one is to remember that what we found, that the magnetic field, while it goes like this on circles around the wire, does not touch it. It goes in circles. It changes as 1/t. Now you can say, as you pointed out very accurately in charges, that as I go very, very close to the wire, it seems that this one goes to infinity. Well, obviously that's an outcome of this. It will never go on infinity, even if you touch the wire. A lot of times though, there are no exposed wires, all right, as you know that. There are no exposed wires. Every wire, when I show you, even the HDMI connector, everything has a shield around it, dielectric or even metallic. Usually, mostly dielectric if there are DC currents. If you want to do metallic, which we call a coaxial line, yes, you have a metallic. So you will never go and touch the current that flows on the wire. However, it is true that as close as you go, that becomes higher and higher. Keep that in mind. Because at the end, what matters in circuit design, when we go from 3D to symbolic and we find capacitors and inductors, is not the value of the electric field for capacitors or the magnetic field and how it is on the chart that matters. What matters in inductance is the flux. So all of the, the area, all of the area around, or in whatever you define it, in this case, because the wire goes like this, the current is gonna be, the flux is gonna be whatever goes if I cut it along the axis, then all the field lines will enter, all right? So flux in that case will be how much of these magnetic lines are entering through an area. The total thing. When you start getting the total effect, like integrate, all of these issues of 1/d going to infinity will disappear. So even if we see that some of our formulas are problematic and approximate, I mean, of course, there are formulas that we develop easily from Gauss's law. We don't pay attention to some singularities, as we say, because when V goes to 0, that is going to create a singularity goes to infinity. It does not, and the singularities do not exist, all right, obviously, in real life. But in that case, what you're going to see is that what matters really is the flux. And the flux never goes to infinity. So your inductance is called, what happens locally is not as critical to the flux overall. All right, so inductance, capacitances are important. In any case, I want to point this out because, as you will see later, I will show you an example. In fact, I think also, even in your homework, the homework that I gave you, the team homework, so you can discuss it as a group, is to practically address that issue indirectly. In any case, so this is what we have seen. Now, the next question that comes in mind is, what is going to happen if I have two currents that go in the same direction first? Let me see if I can see same direction. I will do it here. Let's assume that I have two currents that go in the same direction here. Because, and then I will show you what kind of example what kind of circuit this one can, circuit issue this one can address. Let's assume that these two go in the same direction first. So what here? So the fields will both, in both cases, will go like this. Let me see. All right. So what happens with these lines is that the field in between cancels out, because in fact it is like you see here. If I were to consider with X the lines that go in and with the dot the lines that come out, you see that the field lines, and I have not taken it to infinity as you can see here, I've taken it to a large value. The field lines change. All right, they go, they alternate. And as a matter of fact, because they overlap also, all right, because you will use superposition, they will start canceling out. And because the two are the same current, they will totally cancel out at the center, and they will have the superposition of the two problems is intact. Exactly is going to show you that most of the field in this particular case is outside of the two wires. So two wires that send current along the same direction, they spill their magnetic fields outside. Now, is that a problem? Yes. Why is that? Because if I go to what I showed you before, okay, if I go to this problem, and here, I'm a designer and I look at these two lines, and let's assume that I have, I don't know exactly what kind of circuit it is, but I assume that you have here currents that flow into the same direction. What is going to happen? They are going to spill because they are on the same direction, they're very close to each other. There's going to be zero field in between, and most of the field will be outside. And I don't like that. Why is that? Because if I have magnetic field outside, then I'm going to impact those lines here that also carry current. So if magnetic fields from different lines out here are impacted on the ground, we have magnetic field lines, you know, around this one, and that is going to create parasitic inductances. Every time your magnetic field spills over, you have a parasitic inductance. So in that case, I cannot afford that when my lines are too close. Okay, so that is one thing. You cannot have lines which are too close and the currents to flow in the same direction. Now let's go back to where we were today and see, is there any other way to do this? And the other way, this is, I don't want to erase that, so put this here and then put that here. The other way is to come here and change the direction of the currents. All right, if I change that direction here, and I make the current go to the opposite direction, then what happens? These lines, magnetic field changes its own direction without necessarily changing anything else. It's going to flip, and it's going to go along this direction. Okay? What happens? So this is case A, and this is A, and this is case B, and we go here. This is case B. The interesting thing is that the lines, first of all, in here, between the conductor, between the two currents, flow into the same direction. And outside of the currents flow in opposite directions, all right? Because I'll show you here why. So let's take this line, which is bigger, and goes, well, not exactly. Let's go take this line, which is bigger. All right. And then C. All right. Here. And then take this line from this one. And so this one is going to go like this. And this one is going to go like that. All right, so all of the lines outside of the wires will have opposite direction, which means in case B, then the magnetic field lines, if I just have it there and I see what is coming out and what's going in, it's only in between the two conductors when all of the lines are going in, and therefore they sum up. So they give something like this here, the maximum, and outside they go down to 0. So what do? That means that if I change the direction of the two currents, then I can control the couple, obviously, because the magnetic fields are coupling here, which means they have a coupling inductance. But I can control it because there are only two lines. So I can write about this, that there is a coupling inductance in my circuit, but they're not going to couple to the rest of the circuit, which I cannot control. So practically, if I go to this, I can design, see, I can design these two, or even these three, to have coupling inductances per unit length, and I can incorporate it in the solution, but then I don't worry about this, I don't worry about this, I don't worry about anything here, which in fact, it would have been the case if all of the currents here were all going along the same direction. So now I can have this going like this go like that, and this going like this, and practically the inductance is gonna be, if there is an inductance, it's gonna be all localized. So that's how we do circuits, all right? And that's why the fundamentals that we learn are important. They're not just for us to spend our time talking about them. They are because they introduce, now I know in my whole career as a circuit designer, I know the two lines that have the same current have a problem in terms of creating, parasitic inductances everywhere. So I will never design them. This is a fundamental thinking, all right? And comes out of something very simple. All right. Now let's see. So we talked about a infinite line current, and we talked about the proximity of two of them, all right, and what happens. And then we're going to talk about mutual inductances later, in this class. Let's see now what happens when you have two circular loops, all right? Now, of course, it depends on how you have them, but the closest, if you have two circular loops, and if you want to really have the inductances interact, so you increase the inductance. So for example, if you bring two lines together with the same current, you increase the inductance of that system because the two magnetic fields sum up in between them, all right? So the two together have more inductance than one of them. And plus, they have very little coupling inductance to other parts. Two loops. If you have two loops on the same surface, they don't interact very much because they have a lot of area. And then the moment you try to bring them like this, so they don't touch, already their centers are far away. So there is little coupling between two loops if you bring them like horizontally on the same plane. However, if you take one loop here on one plane and another loop underneath it, then some interesting things happen. All right, first of all, before we go and see what is happening, I wanted to remind you of what we see when we have a loop as opposed to a line. When we have loops, when you have one loop here with this current that flows, again, you're going to use the right-hand rule to see which direction the magnetic field goes. So the magnetic field goes is going to have these lines. However, I mean, the lines are curving out. However, if you go on the surface of the loop, you see that all the lines will be perpendicular. Do you see that? They have to cross the surface of the loop perpendicularly, even if they bend out much faster or a lot slower. But they are perpendicular. They are perpendicular when they cross the loop. And they all cross the loop inside for this current. From underneath, they go above, all right? So the direction is along the positive Z on the surface of the loop. So on the surface of the loop, you only have a Z component, nothing else. And it all goes positive Z for that direction of the current. And if you bring another one, similar to this but below, then you see also that the current flows in the same direction. So again, you're going to have very similar directions in the magnetic fields. Now, if you bring, here I have drawn the two, like in a distance, but in reality, and these are the magnetic fields, all right? And if you go along the Z direction, or for the combination of the two, you can sum the two magnetic fields that we have already found. And then you can sum them practically. Here I have taken as the beginning of the Z direction of the coordinate system. I have considered the center between the two loops, the midpoint along the Z direction between the two centers of the loops. I have considered that as the point where Z equals 0. If you do that, so I can write here, at this point, Z equals 0. Okay, that's what I have considered. If you do that, then practically you can write the magnetic field from the first loop, the magnetic field from the second loop, and then at that point, A, the total of the two is here. All right, so practically it becomes double. However, if I bring, but it happens like this only along the Z direction. If they're far away, you are losing field because it goes like this, all right? If the two loops are far away, all of this field here, and there you're losing it. It goes out. It does not interact very much with this field here. But if I bring them very close, like we do in a loop inductor, where you have all of these loops very close to each other, what happens? All of these lines will flow not only through this loop, but also through this one. Assume that the two come very, very close, but they don't touch. They come very close, but they don't touch. So like this. Okay, that's what, this is the beginning of thinking of a loop inductor. So what happens here is that if I bring a lot of loops together, what goes through this common and more surface of this multi-loop structure, they're all very close together, is a field which is the number of the loops times the magnetic field from each loop. That is one fundamental concept for a loop inductor. All right, and then, so from here, what I would like to do is to go and introduce the concept of the inductance. And you remember what I said? I said that inductance does not, it does depend on the magnetic field, but not on specifically on the value of the magnetic field. It depends on how many of these magnetic field lines, how much flux, as we say. B is the magnetic flux density, right? It depends on how much flux goes through the area of that loop. So we define the magnetic flux density as, that goes through this area, right, as the surface integral, of the magnetic flux density inner product with the area, the surface that I have defined. That is the flux through the surface. Now, if I select the surface to only enclose part of the magnetic flux, not all of it. So if I, for example, let's assume that this is, well, let's assume that this magnetic field is generated by this current, all right, I. All right, this is, let's assume, in fact, let me do it a little better here. Let me see what time it is, okay? Let us assume that this is generated by this current. So we know that this current is going to generate magnetic field that looks like that. Okay, and so forth. Something like this. Okay, have to draw it a little bit. So the magnetic field, if this area is far from my loop, then it's gonna only capture part of the magnetic field line, all right? So usually, and that of course is a flux, but it's not the total flux that is generated by the loop. So it's part of the flux. And as long as I know that it's part of the flux, I can say it, but it's of no use. Usually, if I wanna define the inductance of these, I will have to go and capture the whole flux. And how will I capture the whole flux? I will have to make sure that this area is just the area of the loop that produces the magnetic field. All right, so next, if I, therefore, let me see. So let me write here. If I have a magnetic and electric current, as I said, as I showed before, not that. All right, and this one carries a magnetic and electric current like this. Then the magnetic field lines, as we know, go like that. Okay. So the best way, and there are, of course, they are going like this here. The best way to capture the magnetic flux, the total flux for this field, all right, is to do what? To go and define as area this one. Because if I define as my area, the area of the loop, then practically I can capture all of the field lines because they all go through the area of the loop. Do you see that? There is no field line. If I do this, I have captured them all. In that case, I don't miss any of the field lines, which means that if this current here is I, and if this area is S, then I have to define a direction for this area, which is this. And if this is my Z direction, and here is gonna be the same, with A sub z, which is the unit vector along the z direction. And then my flux for the loop now is going to be the integral over these surfaces of B dot ds. But on the surface of the loop, B is equal to B sub z, A sub z. So it's along only the z direction. So on that loop surface, so S loop. All right. So on that B then becomes A sub z, B sub z, which is then A sub z, assuming mu sub naught. And then let's see the expression for the magnetic field we found here. Let's use this one, not this one. Do we have another one? Okay. It says it's this is going to be mu I over 2a. That's what we said it's going to be. Mu I over 2a, where a is the radius. This is going to be therefore 2a. All right. And that is B. Then if I take that and integrate it over the surface of the loop let's assume is circular, then my flux over this loop is going to be P A squared mu naught I over 2a. And therefore it's going to be mu naught P A I. All right. Just going to make sure that I have correct the magnetic field value here. If I put H equals 0 here, I put H equals 0 is 2 a third, yeah, 2a. All right. So then how do I find an inductance for this? I define the inductance of that loop, L, as psi sub over the loop divided by the current. Therefore, this is going to be mu naught pi a. And therefore, now I have defined a, yes? Yes, thank you. Forgot the two. Okay, thank you. And therefore now I defined a circuit element for this loop. So what does that mean? If instead of this loop, of course, you don't have isolated loops, all right? If I want to create a loop like that, it's gonna show like this. A loop like this, I'm gonna feed it in this form. Okay, so now let's talk about that. 1 second, let me see. Sorry, that does not look good. Let me do one like that, okay? Do it like this. And then, do that. And then I'm gonna take 2 lines and connect them like this. All right, now that's a loop. Let's see why do we do it like this and what it means. If I have a battery here. That's a simple problem, all right? Plus, minus. So here, there is current that flows like that, goes around the loop like this, and comes back. So what is the interesting thing? These lines are going to be very close to each other. This distance here is very small. So this distance, say D, I'll use another one, T. This distance between the lines, T, is very small, almost goes to 0, but they don't touch, obviously. Okay, what happens therefore is this current that flows like this now is gonna force the magnetic field to go through the loop towards down. So I'm gonna have now field lines that will look like this. All right, it will look like this. And they will all have this direction, which is, if I assume this is Z, then that's going to be the negative Z. But these are the magnetic field lines. What happens in between the two currents? Since the two currents are flowing in the opposite direction, you remember what I said before? That only in between them, the fields will be strong, and outside will be very hot, like practically they will cancel out. Since the two currents flow in opposite directions, the currents out here, the magnetic fields out here will cancel out. So I don't have any contribution to flux from here, because the flux, it implies the fields will come out, they will go in like that, but this is so narrow that the contribution, the flux, not the magnetic field, but the integral of the magnetic field here over this area, which is so narrow compared to this, is going to be practically 0. So all of the flux in this particular geometry comes from the loop. All right, and I found it. So now in this circuit, I can, if you tell me what do I see from the source, I can ask you, what do you see from points A and B? Then the symbolic representation of that is plus here. And then I have one loop, but this is an inductance. That's the symbolic representation. So what I see is an inductance which has this value. All right. Now we're going to be ready, before we go to other more complex structures, to talk about the inductance. If this loop has multiple, it creates multiple loops. Let us, we'll do it next time. We don't have time right now. But I wanted to just show you of exactly how we simplify a geometry like that and how the equivalent circuit eventually comes to this form. All right. And then we're going to see, because these are small values of the inductance, and usually we need more inductance for circuit design. What do we do to increase the inductance? Obviously, what you do is to create more loops, all right? Because if you create more loops, then you create more of a field, but it's not going to be just N. If you create N loops, you gain in flux and inductance N squared, but we'll discuss that next. Yes, it does not seem like that, but we'll show it next time, okay? So that's for today. What I wanted to do is give you a problem, an exercise. So we need to go. And then you will have it for Wednesday. I will activate it right now. If I find where is here. Okay. There. Here. There. Go to this. Come on. Exercises. This I have to unassign. This is, okay, here. I'll give you this for Wednesday. All right. Okay. Any questions please try to make it to the office hours today. We're going to start solving problems. Okay, for those of you who don't have any access, and I will record it also.
What time is the office
If I
hour?
put out there, the worse it gets. Yes. Any questions?
What time is the office hour?
A question about Zoom. Yes, tell me a question.
What time is the office hour?
It's from 3:30 to 5:30.
Okay. Okay.
Same time. They are on those office hours have been on Canvas forever. All right. 3:30 to 5:30.